Okay, welcome one and all. So in this lecture, we will discuss or I will discuss the normal approximation to the binomial. Okay, so this topic we are going to discuss. So basically the theorem or result which is working behind this concept of normal approximation to the binomial, it is here. Suppose we have a random variable x, this random variable x, it is a binomial variate. This x, it is a binomial variate or binomial variable, okay? And whose mean it is NP, which will be denoted by mu, and whose variance is NPQ, which is denoted by sigma square. We all know that if x is a any random binomial variate or variable, then its mean value, which we denote by expected value of x, it is n into p, and its variance, it is given by npq. Okay, this we already know. So same thing is mentioned here. So what is n here? N is the total number of independent Bernoulli trials. Okay, so what is n here? It is total number of independent Bernoulli trials. And we know what is Bernoulli trial, a trial which results in exactly two outcomes. A trial which results in exactly two outcomes. One of them we term as success, the another we term as failure. Okay. And what is the P? P here, it is the probability of success in a single trial. This P, it is the probability of success in a single trial, which must be constant throughout the our trials. Throughout means for all the trials, this P, the probability of success must be constant. And what is Q? It is the probability of failure for a single trial. Okay, so just wait, please. Okay, so here we have x, which is binomial variate. Now, if we construct a new variable, which is given by this x minus np, basically this is nothing but x minus mu divided by this sigma. So this is nothing but this, or this is x minus expectation x, okay, divide by standard deviation of x. Okay, so we are creating a new variable, new random variable, which is x minus mean of x, mean of the same x, divided by the standard deviation of the same random variable x. Okay, so if we are creating this random variable, then this random variable, new random variable, z, we are giving a symbol z or z, then it will follow a standard normal distribution. Means this z, okay, this will have a standard, means this z, it will follow normal distribution with mean 0 and 1. Okay, but provided the n, okay, the number of trials, it should be sufficiently large. N tends to infinity means n should be sufficiently large, or n should be large enough number of independent Bernoulli trials. Okay, so what is important here, that this x, this is a binomial variate. Okay, but this z, z or z, this will be a normal variate. I repeat, x is a binomial variate, and what is z or z? This is will be a normal variate. Okay, but provided this n, it is sufficiently large enough. Okay, so this result, it is working. This is the base behind this concept of normal approximation to the binomial. Okay. Uh, Okay, so now actually this z, its mean expected value of z, it will be 0, and its variance of z, it will be 1. Actually this z, it is nothing but the standard normal variate. This z, it is nothing but standard normal variate. Now this result we have already discussed during our proved, rather we have proved during our lectures. Okay, so now uh, what is this? normal approximation to binomial. Actually, to those cases or physical situation, to those cases or physical situation where we can apply binomial distribution, where we can apply binomial distribution to find a certain probability. Okay. To the same cases or situation means we what we do, what is the concept? So one probability which will be calculated by binomial distribution. Okay. The same probability we can find by normal distribution also. Okay. The probabilities means the probability which we can find by binomial distribution. The same probability we can find or calculate by normal distribution also. But this probability which is calculated by normal distribution, it will not be exactly equal to this. It will not be exactly equal. It will be approximately equal. I repeat, what is this concept of normal approximation to the binomial distribution? To those cases or situations where we can find a certain probability, to those cases or situations where we can find a certain probability using binomial distribution, uh, to the same cases means the same probability can be calculated by normal distribution by applying normal distribution, but the probability calculated by normal distribution, it will not be exactly equal to this probability, rather it will be approximately equal. Okay, so what's the meaning? So for the meaning, here in this graph, there are two type of graphs here. One, we can say one are histograms, these rectangles. Okay, these rectangles, one can see these rectangles, they are histograms. And the area of any such histogram, I repeat, the total area of any such histogram, it represents the probability. It represents the probability under binomial distribution. For example, if I talk about this one, this area, actually what this area is, it is nothing but probability that x, the binomial variate, it takes the value 7. So this will be ncx p raised to power x and q n minus x. Okay. Uh, so here, what is our n? N is 15 number of trials. Okay. And what is p? It is 0.4. Okay. And what is q? It is 0.6. So here one can easily calculate that what is this probability. And this probability, it is nothing but the area also. This is nothing but the area. Area, which is area of the rectangle or histogram, which is above this 7. Similarly, what is this one? This one, this area, it is nothing but this area, it is nothing but probability that x takes the value 4. The binomial variate, x takes the value 4. Okay, so this is one graph. Okay, the histogram. Now there is another graph there, which is in the blue color. Actually, this is the normal probability curve. Okay, we have already discussed during our lectures that this graph, it is a normal, the bell-shaped, inverted bell-shaped curve. This one. So actually, this curve has been drawn by taking the mean 6, okay, mu, which is the mean of the binomial variate also, and by taking the sigma square variance as 3.6. Means this curve, this blue colored curve, this normal probability curve, it has been drawn by assuming that, by taking that the mean is 6, mean of this normal distribution is 6, and the variance of this normal distribution is 3.6. Now we can draw these both the graphs. This we will, how we can draw this, we will see in our activity under Excel, Microsoft Excel. Okay, so this we will see short in that lecture. So basically, what is this graph? It is the superimposition. This is the superimposition of two graphs, one normal curve and the another, which is the histogram. histogram, which means these are rectangles which are histogram. Okay, and the area under histogram, it represents the exact probability. Okay, the exact probability under binomial distribution. And if I talk about this area, just if I talk about this area, just under this curve, this normal probability curve. So what is this area? It actually, this area, if I say this is probability, not x, it should not be x, it is probability z or z. Uh, it is area under this one. It is Z or Z. Okay, this I discuss in the next one. Don't worry, this I am discussing. Okay, so here basically we have this graph, which is superimposition of normal curve and the histogram, which represents binomial distribution. So now. Now suppose I need this probability that x takes the value 4. So what will be that probability? B, x, and p. So this is B, x, and p. So it is nothing but a probability that x takes the value x, which is nothing but ncx, p raised to power x and q raised to power n minus x. So what is the value of x? Number of successes. It is 4. The number of successes, 4 number of successes in 15 number of trials, and zero point 0.4 is the probability of success in a single trial. Okay, so this one can calculate. Okay, just substitute n15, x equal to 4, p equal to 0.4, q equal 0.6. If you calculate, this will come out to be this one. So this is the probability for binomial distribution. So actually, what will be this probability? This will be this total area. Please mind, this will be the total area. Okay, which is above this value 4. Okay, so what is this 0.1268? It is the total area. Okay, under this. Now, if you look carefully, I can find the same area, but it will not be exactly equal. But I can find approximate, means I can approximate this area under normal probability curve also. So for that, so uh, yes. So actually the total area is this one. But if I calculate this area, if you look carefully, this area means below this normal curve. Okay, this black colored normal curve. Then even this area, it is approximately equal to total area. Okay, so I am talking about this area. Okay, so now both the areas they are not exactly equal, but they are approximately equal. Now, to find this area, which is under normal curve, what we need these two ordinates, x1 equal to 3.4 and this one. Why so? If you look carefully here, what is this 4? It is just the midpoint of this histogram or rectangle. What is this? Look at the position of 5. It is just at the midpoint. Even 6, it is at the midpoint. 7, even it is the midpoint. Midpoint, it is at the midpoint of the rectangles or histogram. So what will be this point? I am talking about this point. This point will be 3.5. And what will be this point? It will be 4.5. Okay. So if I have to find or approximate, if I have to approximate the area under normal curve, okay, then I need these 2 points, okay, 3.5 and 4.5. So for 3.5 and 4.5, I will have my standard normal values. Okay, this is 3.5 x1. Okay, x1 minus mu. Okay, divide by what is this? It is sigma. Actually, what was our sigma square? If you recall back, this was 3.6. Okay, so what will be sigma? The square root of this 3.6, it will be 1.897. Okay, so actually now we are constructing the variable. The variable is that z or z, it is x minus mu divided by sigma. Okay, that's how we are constructing. So this, what is this? This is the value of z1 or z1, okay, corresponding to this x1. And similarly, we are constructing this 4.5 minus now 4.5, which is x2, and obviously this is our z1, z2. Okay, so look here. So the probability x equal to 4, which is this one, which is nothing but 0.268, it is approximately equal. Approximately equal to what? This probability. Actually, it should have been mentioned that there it should be probability that the x normal variate. Okay, so okay, no, it is all okay. It is all okay. So here, this probability here, it is for this z1, means this one, and this is z2. Okay, so what is this probability? What is this one? It is the exact area or exact probability. This is the exact area or exact probability under the binomial distribution. Okay. And what is this one? It is the approximate area or probability. This is the approximate area or probability which is under the normal distribution. Okay, so now these we can calculate how that this probability, it is nothing but to the entire left of this value, okay, 0.79. Actually, this 4.5, it is corresponding to what? It is corresponding to 0.79. Okay, so I just wait if I can clear all these. Yeah. So this, you can see here, this is at the mid. So what is this point? It is 4.5. 4.5, and this is corresponding to what? This 4.5. It is corresponding to minus 0.79, and this value, okay, it is 3.5, okay, which is corresponding to minus 1.32. Okay, so we are having this entire area, entire left of this one. Okay, this value, which is nothing but this. So actually, it is the CDF value. Okay, for normal probability minus this area, means this entire left of this point, minus 1.32. You can see here. Okay, so now yeah. Now, these values, they are given, they are from the normal probability tables that we have discussed. So from that, we are having this value. And what is that value? This value is 0.1214. And this value here, it is mentioned that this agrees very closely with this value. Means this value, it is approximately equal to this one. Okay. So here we have calculated this value probability that x equal to 4 one time by binomial distribution, which is the exact value of the probability. And we have calculated the same probability, but by normal distribution, but that is not exactly same. That is not exactly equal to this. It is approximately equal to this, this value. So now, yeah. Now we will calculate this probability that x is between 7 to 9, means we are interested in this entire area, means under 7, under 8, okay, and under 9. Okay, so how we are calculating this? Wait, please. Yes. So how we are calculating this? This we are calculating by using binomial distribution. So first we calculate the probability up to 9, means 0 to 9. Okay, means this entire probability which is here. And obviously this value, it will be the CDF value, but for binomial distribution, CDF value. Okay, up to 9. Okay, so actually, what is this value? It is nothing but probability that x is less than equal to 9 minus probability that x is less than equal to 6. Now, what is this thing? This is f at 9. And what is this? This is f at 6. And what is this f? It is CDF, the cumulative distribution function, but for binomial distribution. Binomial. Okay. So we calculate this entire area up to 9. Okay. And we subtract this area, which is up to 6. Okay. Up to 6. Up to 6. Okay. Then that will give us this area. This area. So now once again, just like normal curves, normal tables rather, normal probability tables, we have binomial probability tables also. So these values are from there. So this value, it is the exact value of this probability, but calculated by binomial distribution. Now, now we will try to find the approximate value of the same probability, but using normal distribution. So for that, you can very well see this area will be this one, only this one under this one. So obviously this white colored, you can see this white colored portion, it will be left behind. Okay, so it will not be that. So it will not be exact area. It will be approximately equal. So what we need this point. You can see we need this point. What is this point? It is 6.5. Okay, and we need this point. What is that? It is 9.5. Okay, so to make it clear, one can very well see. So it is this point. It is 6.5. Okay, because 7 minus, because this is at the mid, 7 minus 0.5. And what is this point? It is 9.5, because 9 plus 0.5. Okay, so we need these two coordinates. Okay, 6.5 and 9.5. Okay, you can see. And 6.5 minus mu divided by sigma. Okay, and 9.5 minus mu divided by sigma. Okay, so this is our Z1, this is our Z2, and this is X1 and X2. So once again, we are creating that standard normal variate, that which is Z or Z. This is X minus mu divided by sigma. Okay, so if it is Z1, Z or Z1, then here X1. If it is here Z1 or ZZ2, so this is this one. Okay, so now this probability, which is approximately equal to what? This Z1 and this Z2. So this probability, this is under binomial distribution, and this probability, this is under normal distribution. So once again, we can calculate by the same concept. And now this value, it is pretty close to this value. Okay, this value, which is calculated by using normal distribution, it is close to this one, which is by binomial distribution. So here, uh, so here, now we are stating the result, that if we have to find this probability where x is binomial variate, then this is approximately to the this probability, which is for the standard normal variate. And obviously this will be x1 minus 0.5. Okay, so if you have observed when this in previous example, when this x1 was 7, if you recall that we were having x1 is 7. So what was the value of z1 or z1? It was 7 minus 0.5, which was 6.5. Okay, minus this value, minus 6 the mu, and divide by sigma. Okay, so what was sigma? It was 1.89 something. Okay, similarly, when x2 was 9, x2 was 9, what was z2 or z2? It was 9 plus 0.5. Okay, so this was our point, and minus again 6 and divide by what? 1.89. Okay, so here that's why x1 minus 0.5 and here x2 plus 0.5. Okay, so here here 7 minus 0.5, this was 6.5. Okay, and here it was 9.5. Okay, so I think this must be clear now. And rest is minus NP, this minus NP, the mean 6. Okay, and divide by this standard deviation, which was 1.89. So this is important that here this value x1 minus and this. Okay, so here this 0.5, this is what we call continuity correction. Why it is named? Because x, the binomial distribution, okay, it is a discrete distribution, and the normal distribution is a continuous distribution. So in this concept, what we are doing, we are converting a binomial distribution into a continuous distribution. So for that, if you have by now you must have felt this or observed this, that we are taking the help of this 0.5 to convert the discrete binomial distribution into the continuous normal distribution. So this 0.5 is the continuity correction. Now, here, why continuity correction was 0.5? Because here our interval length, the interval length was 1. Okay, the interval length was 1. So if you go back, yes. So here you see between 2 to 3, what is the interval length? 1. Between 3 to 4, it is 1. 4 to 5, 1. 5 to 6, 1. So this interval length, okay, actually in our Excel activity, we will call it bin. In Excel activity, we will call this bin, this interval length. Please mind, this is important that in Excel activity, this will call bin. Okay, so here bin or interval length is 1. Okay, and correction, the continuity correction, it is 1 divided by 2. 1 divided by 2, that was 0.5. By chance, suppose in some case our this interval length or bin, suppose it is 2. This bin or interval length is 2. So what will be our continuity correction? Divide by 2, it will be 1. Okay. What is this continuity correction? This is nothing but bin or the interval length of the interval divided by 2. Okay. So now going back. So now, actually, if you see in your textbook, the result is given in this form. Okay. Actually, for only x less than equal to x, but I have stated in this form. Okay. You can see here because actually both are same. You can understand this one also and this one. And now, there is a certain remark about this approximation, that this approximation will be good if NP and N1 minus P both are greater than or equal to 5. Okay. Okay. Some authors they say that this NP and N1 minus P that must be greater than or equal to 5, and some say that it should be greater than or equal to 10. Okay, so but we need not to be fuzzy about this. Okay, so both will be for us there. Okay, and the quality of approximation, it is quite good enough if large n means n is large. Actually, here what we are talking about that the two probabilities, one calculated by normal distribution and one calculated by one calculated by binomial and one by normal distribution, their approximation will be pretty close. Okay, that's the meaning is quite good. Okay, uh, means the two probabilities will be close enough if the n is large, and if p is close to half the probability of success, then even the small or moderate values of n, the sample size, okay, even they will also give a good approximation. Okay, I repeat, by chance, if p is not close to half, p is not close to half, then for the approximation to be good, if the p is not close to half, then for good approximation, our n, it should be large enough. But if p is close to half, then even n is small or even moderate, then even it will this concept will give us a good approximation. So now here there is a question. Here we have to find this probability that x is less than 30, and which is nothing but probability x is less than equal to 29. And what is x here? Actually, number of patients which recover, patients which recover from this disease, from the disease. Okay. So, sorry, disease. Okay. So here, for every patient, wait. So for every patient, there are two options. Either the patient will recover or survive the disease, or he or she will not recover or survive the will not recover or survive the disease. I repeat here, for every patient, there are two options available. Either every patient which has contracted this disease, which was affected by this disease, either he will survive this disease or he will not survive this disease. So that's why we can calculate this probability by using binomial distribution also. For that, what we need this probability. So for that, what we need, it will be nothing but summation NCX. So what is n here? 100 means out of total 100. The total n is 100 patients, NCX. And P, what is P? It is zero point 0.4. Okay. So 0.4 raised to power X and 0.6, the probability. And what is our success here? Means what is our success if the patient recovers? Okay. And if the patient doesn't recover, then it is our failure. So here it will be NCX, PXQ, N minus X. And X will be ranging from 0 to 29. Okay. So this will be the exact probability, okay, of this case that out of 100, fewer than 30 survive. Out of 100 such patients which have contracted this disease, fewer than 30 survive. Now, here in this solution, actually, we are calculating its approximate value, the approximate value, but using normal distribution. So here, what will be mu NP? The mu of this mu, it is the mean for normal distribution as well, also as well for the binomial distribution also. This is the mean for normal as well as for binomial, and this is the standard deviation for both normal as well as binomial distribution. So here, in order to find this probability, what we need, if I have to convert this into means the approximate into the normal, it will be z less than z or z less than equal to 29.5. This is bit important where most of the means there is a chance for committing error that someone may take it as 28.5. That will be wrong. Please mind. Uh, uh, Why so? Because if I am trying to, suppose I draw here, okay, the same thing, and suppose I am trying to approximate by the same technique that we were using earlier, okay. Suppose actually now here it will be 29 and here it will be 28 because here once again the bin value or interval length is 1 because here it is number of patients which recover from the disease, okay. So what we need, okay, we need this one. Okay, fewer than, less than equal to 29, less than equal to 29. So that's why we need up to here 29.5. Please mind, because if you go up to 28.5, you will miss the half portion. You can very well see if you are up to 28.5, you will miss some portion. Okay, so it is 29.5. And this figure, it is just for the explaining of this concept that why it should be 29.5, why not 28.5. Okay. Otherwise, this is not a accurate figure. Okay. For this example. Now, rest is the the previous process that here this is our value 29.5 the mu and divided by the sigma, and now this value it will be corresponding to this one, okay, the approximation, okay, so and that is this one from the normal tables. So here there is a MCQ test is there having total 200 questions, each with four possible answers, of which only one is correct. So what's the probability that sheer guesswork means pure guesswork, yields from 25 to 30 correct answers for 80 questions out of 200. Okay, about which the student has no knowledge. Means he's answering the options merely by sheer guesswork. Okay. So here once again, actually, this is the exact value of this probability, which is calculated by binomial distribution, Bx and P. Okay. So please mind here what is N? It is 80. It is not 200. Please mind, it is 80. It is not 200. Okay, and what is P? The probability of success. Okay, here, what is our success? Here, actually, every student has two options. Either he will answer the question correctly or he will not answer the question correctly. Means he will answer the question incorrectly. So here, what is the success if he answers the question correctly? And the probability of success will be 1 by 4. Okay, and so now this one we can calculate because we need this probability that, and we have what X represents number of successes. So I have discussed in during the lectures many times that our X in binomial distribution, the random variable, okay, it represents number of successes, and here our success is if the student answers the question correctly. So X is that. So we need, wait. So we need that he answers questions between 25 to 30. Okay. So this one, this probability, this is the exact value of the probability, but by binomial distribution. And now, once again, we will have our mu, the common mean of normal distribution and binomial, and common standard deviation of normal and binomial. So once again, now we have this Z1, okay, 24.5 minus this mu, mean, okay, and this Z2 or Z2, this minus, once again, same means constructing the same random variables, okay. So here, these are the two values. Now, this is the value which is under binomial, and this is the value which is under normal distribution. And obviously, both are not exactly equal, they are approximately equal. Now, these probabilities, once again, by using the previous process, we can find. So here, this is the approximate value. Okay. So here, in binomial distribution, X, the random variable X, it denotes number of successes. And here our success is that if the question is being answered correctly by the student. Thank you, everyone, one and all.